Alright, to go further with our solution of equations of motion, we need the equations of motion for our airplane. Then we'll go into, well, how do we solve them with Laplace transforms and differential equation techniques. So the airplane is a rigid body. We're going to assume it's rigid. Not completely true, but that's the simplest version of the equations of motion. If you want to get more into non-rigid aircraft, then take a class called aeroelasticity, a graduate level class. Alright, so an airplane has 6 degrees of freedom. It has a forward velocity, side velocity, and vertical velocity. And we've talked about these before. This is the velocity vector of the airplane. And then it has angular rates, roll, which is P, pitch, which is Q, and yaw, which is R. So this is a rigid body in a three-dimensional space. And these are called the angular rates, or the angular velocity, omega, P, Q, and R. So those are the state variables of the aircraft, the motion variables. And then, of course, we have forces. We're going to be applying Newton's law, so some of the forces equals mass times acceleration, etc. So we could have gravity, aerodynamic forces, and propulsion forces. Alright, so let's move into how do we get the equations of motion. The first thing I wanted to look at was a picture of the airplane in 2 different axis systems. The airplane can be in the Earth-fixed axis system, with the origin located somewhere on the Earth. Usually X is pointed north and Y is pointed east. And then with a right-handed coordinate system, Z is pointed down. And then the aircraft can be located relative to the origin of the Earth-fixed axis system, pointed to by a position vector RC that points to the C, a point on the aircraft. And usually this is chosen to be the center of gravity. There's various reasons for that. Some of those you learned in dynamics, that you can describe a distributed body, a rigid body, as rotating and moving with its center of gravity, center of mass. Alright, so then the airplane has body fixed axis system, which we've been talking about since the beginning of class. So there's an X, Y, Z axis system attached to the airplane. X out the nose, Y out the right wing, and then Z pointed down, located at the center of gravity. And then the airplane center of gravity has a velocity V, and that velocity can be expressed either in the Earth-fixed axis system, or usually we talk about it in the body fixed, which is U, V, and W. So these are the variables. There's a picture of the variables on the airplane. And again, in the body fixed axis system, we have U, V, and W, the forward velocity, the side velocity, and the vertical velocity. And those would, because their velocities, they're X dot, Y dot, Z dot, they're derivatives of the position of the aircraft in the body fixed axis system. You can also have the velocities in Earth fixed axis system, and that would be XE dot, YE dot, and ZE dot. And one of the main reasons you might want to calculate these is if you wanted to trace out the path, the flight path of the aircraft, that would be in the Earth fixed axis system. In other words, if you took off from Wichita and flew to San Diego, there would be a flight path in the Earth fixed coordinate system. You could integrate these velocities and figure out where the airplane went as a function of time. Alright, Newton's laws for a rigid body, and it's key that we're talking a rigid body, because if it's non-rigid, a bunch of extra terms get put into the equation. So in the Earth-fixed coordinate system, it's easy, because this is an inertial reference frame. We know that, or we're assuming it is, even though the Earth spins about its own axis and goes around the Sun, and the Sun goes around the center of the galaxy, and the galaxy is moving through space. But assuming it's an inertial reference frame, the sum of the forces in the Earth-fixed axis is equal to the change in time, the change in linear momentum, which is mass times velocity with respect to time. So that's just fundamental Newton's law. And of course, if the mass is not changing, you can pull that outside, but I'm writing it in the general form here. That's in the Earth fixed axis system. In the body fixed axis system, you learned in dynamics as well as in AE 415 that in the body fixed axis system, because it's rotating, it's a non-inertial frame that if we want to express the change in linear momentum, we have to include not only VB dot, but because the XYZ axis system is rotating, we have to include an extra term that contains the angular rotations of that axis system. So we typically want to derive our equations of motion in the body fixed axis system because we know all the aerodynamic forces and moments in that axis system. We know lift is up, drag is backwards, and side force is sideways. All right, so we'll be using that set of equations in the Earth fixed axis system. And then angular momentum equation. This is the sum of the moments is the change equal to the change in angular momentum, h. And in the body fixed axis system, again we have h dot, and then we have omega cross h because h is expressed in this rotating reference frame. And then in dynamics, you went through the derivation, or you talked through the derivation, that the angular momentum of a rigid body is described by its angular velocity times this thing called the mass moment of inertia matrix. And one of the advantages of using the body fixed axis system is that this inertia matrix is constant because it's done in a body fixed axis system. So that axis system rotates with the airplane, so the wing is always to the right, the tail is always behind, and so these integrals that go into the inertia matrix are the same no matter what the orientation of the airplane is. So HB dot is just going to be IB, there's no derivative here, times omega dot in the body fixed axis system. So this is the number 2 reason that we want to stick in the body fixed axis system. And this is actually bigger than the fact that the forces and moments are easier in the body fixed axis system. All right, so we have an equation for the force. Here's our force equation, and then here's our moment equation. And so we need to substitute in for omega, and we need to substitute in for omega here, and for omega here, and for the velocities, and calculate the equations of motion. So omega is pi plus qj plus rk, or pqr, and then here is the inertia, mass moment of inertia matrix. It has these terms that you studied before, ixx, Iyy, and Izz, and then the cross products like Ixc and so on. Turns out most aircraft are symmetrical, but don't look at this now because we're going to add this in later. That's why it says later here. And here's the definitions of those. Ixx is the mass and its distance away from the x-axis. So if you have an x-axis, you take the distance away times a little mass, and then you add it all up. So this represents the distribution of mass relative to the x-axis. And then the cross product, well, here's the Iyy, same deal away from the y-axis and z-axis. And then the cross products are the ones that have like x times y, x times z, and y times z. We're not going to go into any more detail on this. You did this in dynamics. If you take 714, the follow-on senior level elective next fall, we'll go through an actual derivation, again, just to remind you how this all works, of how this thing is. All right, so now using the body fixed axis system, we're going to do the force equation. So we're going to substitute in for omega, substitute in for velocity, substitute in for velocity, and get the terms down here. So we need to take omega cross VB, and then we need to take VB dot, which is just going to be U dot, V dot, and W dot. And the forces we're going to say right now, still need to figure these out, but we're going to say Fx is in the X, Fy and Fc are in the Y and Z. Eventually we'll have to relate lift and drag to Fz and Fx, and side force to Fy. Alright, so you can choose your own favorite method of taking this cross product. You can brute force it, and just I cross J is K, K cross J is negative I, and so on. Or you can do this determinant method, which I think is what most of you guys learn nowadays. So you put ijk up here, you put the first vector here and the second vector here, and then you take the determinant. So you get I times the determinant of this. So that's this term, I times QW minus VR. And then you take the expand out the determinant about J, and you get this times this. So this is minus J, because it's the second term of the determinant, PW minus UR. And then we expand about K, and we get this term here. Alright, so once that's done, we get this term here. Here's the I term, here's the J term, and here's the K term. And then here's U dot, V dot, and W dot. So this set is the force equations of motion. So this is the X equation, this is the Y, and this is the Z. Alright, so now we need to do the moment equation, which says that the sum of the moments is equal to the angular momentum dot, and then omega cross h. So this is the body fixed axis formula. And the moments we're going to just call, we've used this terminology before, rolling moment, pitching moment, yawing moment. This is the hard one to calculate. It's the omega cross h, because h is this thing, which is this matrix times this vector. So you take this vector, multiply it through, and you get a vector, a column vector that has p times ix, q times ixy, and r times ixz, and so on. So you get a vector there, and then you have to cross product it with omega up here. The other term's not too bad. We talked about this before, that HB dot is just IB omega dot, because I is constant in the body fixed axis system. Alright, so here's the whole thing that we need to calculate. We plug in Lm and N on the left, that's the sum of the moments. Here's the matrix here. This is omega dot. And then we have to calculate this thing here. It's omega cross I times omega. After a bunch of algebra, which guess what? You get to do this in homework. So I'm posting a new homework set that is going to involve you carrying out this cross product. It's not really that bad. Just take your time, check with friends, make sure you check your signs as you do it and your terms, and you'll be good. But when it's all done, you get this set of equations. Pretty complicated, but the way you can identify these if you don't see the L, M, and N, because L is obviously roll, is you look at this, and this has a P dot times the principal moment of inertia. And notice this is, I switched to the book's notation. They use IX instead of IXX. I don't know why it was hard for them to write the extra X, but that's how they did it. So the principal moment of inertia multiplies the rate in the axis that we're in. Now we do have some r dots over here and q dots, but notice those are times the products of inertia, the cross products. So this is the rolling moment equation, this is the pitch, and this is the yaw. There's pitch and yaw. And notice pitch is times q dot, and yaw is times r dot times the principal moments. And here's where we wrap things up. We say, oh, most aircraft have a real strong symmetry. They're symmetrical about the XZ plane. And so if you remember, the XZ plane is, there's our axis, there's X. It will soon be X. And there is Z. So this plane, not airplane, but the plane, the mathematical plane, if you look, you have the wing on this side and the wing on this side, and if I could draw with the mouse, those wings would be identical, and so the plane is symmetrical sideways. And what that means is that those cross product of inertias that contain y, you get the same mass on the right side as you do on the left side, and it cancels out when you do the calculation of IYZ or IYX. And so we can knock those terms out of the previous set of equations. So all of these inertias that have y in them, those terms go away. You get the idea. And we get a much simpler set of equations. And so this is the set we're going to use. We're always going to assume symmetry about the XZ plane, and the equations become simpler. Which is good, because expressing this stuff over here, the moments, takes some time even with the simplified right-hand side. So next lecture we'll be talking about, well, what goes on this side, and especially in the force equation, what forces go into this equation.